thank you all for coming. Thank you for inviting me, for hosting me the past few days. It was a pleasure to be here with you. And yeah, okay, so this presentation is kind of going to be about a couple of papers on the topic of block ciphers, one of the topics that's very dear to my heart. And yeah, let's get started. So the title is Theorized Independence of Block Ciphers. I think I should tell you what I mean by block ciphers first. For this talk, it's going to be practical encryption schemes. For example, and one of the main stars of this talk is going to be the Advanced Encryption Standard. And for this talk, I'm going to be talking about symmetric encryption schemes, where we have two users, they share a secret key, SK, and then they use the encryption algorithm ENC to encrypt their message along with the secret key. This spits out the ciphertext, you send to the other person has the same secret key, so they can encrypt and they get the message. Okay, so let me give you some information about AES, which I don't know much, but I call it from Wikipedia, so you know it's true. So it's a specification for encrypting electronic data. It's been around since 2001. It was selected after a 5-year standardization process against 14 other designs. It became US federal government standard and the first and only publicly accessible cipher approved by NSA for top secret information. Sounds very cool, actually. I didn't know these things. So the summary is that AES is very important. It's used everywhere, all the time. So if we trust it so much, we must know it's secure, right?
Just a quick question. What was the other standard? I keep thinking of a different acronym.
DES?
DES, yes, DES. What's the relation between this and DES?
Yeah, so DES was before AES. I think it was
proposed by IBM and it was broken. So DES was proposed by IBM in the 70s. And then I think at some point it was 56 bits, and at some point we reached computational capabilities beyond it. And so I think their recommendation was to double the key length, but then they found like clever meet in the middle attacks where with double key length you don't get double security. So yeah.
Okay, sorry, that's just.
No, that's good. Honestly, I don't know much about the history either, so very happy that someone knew what changing. So, but yeah, the question here is about security. So, first of all, what does it mean to be secure? And as cryptographers traditions, we like to use reductions. If you want to show, for example, that the encryption scheme is secure, what do? You need a mathematical problem that people believe is hard because it has withstood the efforts of smart people for some time. We have examples, LWE, DDH, have a bunch of those. And then what do? You proceed by contradiction. You say, let's say there exists an adversary that can break this encryption scheme S. Then you're going to use the same adversary or some related adversary to also solve that mathematical problem P. And we believe that's not possible, so contradiction. We sleep safe at night knowing that this mathematical problem is solved. And it's crucial here that A breaks security of S, then it can also solve the mathematical problem, which means that the encryption scheme and the mathematical problem must share some structure. So, okay, well, if we want to show AES is secure by reduction, we just need to find some math problem that looks like AES. Okay, simple enough. I reminded you of some nice problems we believe are hard, so let's look at AES. So that's a meme I got from the internet that tries to explain how complicated this AES is. So I don't know about you, but it doesn't seem like a math problem that looks hard to me. Of course, okay, that's a meme. We shouldn't base anything on memes. Let's try to get a more theory-friendly description first. So I put the image of our setup, this encryption scenario at the top. And what I'm describing AES, what I'm describing is basically this encryption algorithm, which takes as input the secret key and the message, and it should give us the ciphertext. And so block ciphers generally, they're supposed to be fast, efficient, so they're going to happen in rounds. And for this, we're going to assume that the secret key has as many parts as the number of rounds. Actually, one more, I have a 0 there, but it's fine. And yeah, so every round we modify the message a little bit, and then at the end we spit out the result. And this is a general philosophy for block ciphers that every round is like a simple, easy permutation, and the hope is that by composing many of them, it becomes indistinguishable from random, and we get secure. So to describe AES, here is like the framework that one could use to build a block cipher. This is going to be your input, and We have here, let's say, 4 rounds. We have 5 parts to our key. And yeah, okay, so we put in a message M. So this will be here. First step, we XOR with a random key. So we get M plus key 0. And then there is this permutation that's public, everybody knows it, that maps N bits to N bits. And we apply it to this M XOR key 0. So we get this different N bit string. And we keep going. We XOR with a new key 1. We apply the same public permutation pi that everybody knows. And at the end, we get the ciphertext, and that's what we use. And also, if you want to decrypt, you start from the ciphertext, and you start undoing things. You know the secret key, so you can XOR them one by one, and the permutation pi is public, so you can. Okay, so AS uses the following paradigm, which uses that framework, called substitution-permutation network, which says, instead of having this huge public permutation on N bits, you're gonna, for efficiency, you're gonna break your input, which is N bits, into K blocks, that's where K comes, of B bits each.
Can I ask a question? Sorry. That algorithm is incredibly easy to break, right? All you do is just XOR the keys together, permute it, and then all it does is XOR the bits with a certain number.
So when I say permutation, I don't mean of the bits, I mean of the whole bit stream.
Oh, I see.
It's like a permutation on the space.
It's just a one-to-one map
Yeah.
between n-bit vectors.
Yeah, and actually that's why, this could be very expensive to describe. That's why you can't just use any pi, a random pi, because you need many bits to describe this.
Okay.
And that's why we're gonna see this way of getting this permutation, where you're gonna get, again, a public permutation over a smaller domain, over B bits now. It's gonna be the same one. And I'm gonna tell you which one is used usually. And then we apply linear mixing. So note that the XOR and these S boxes, they apply to every block separately. So you somehow need to mix the blocks between them. And this is what the linear mixing does. We have K blocks here. So the linear mixing is gonna be a K by K matrix. So here will be a 4 by 4 that kind of gets linear combinations of the blocks and rearranges them. Yeah.
So in this paradigm, how long is the secret key?
So the secret key will be the length of the input times the number of rounds. I will say that usually the length of the secret key is exactly the length of the input, and you use a key scheduler to expand by the number of rounds. And it's an open problem to kind of analyze what the key scheduler does and everything. But for the purposes of theory, we're going to assume we have independent keys per round.
So maybe what I'm confused here, does linear mixing rely on secret key?
No, it's a public matrix, public permutation.
So in this graph, only S uses secret key.
No, the S is also not secret. Okay, so look at here. What I am substituting is the public permutation pi. The XOR is still happening.
So secret key is still, you just XOR it.
Yeah.
This is literally just some way of writing
pi.
a pot, like a permutation on n bits.
Yes.
Like one, as you said, a random one might be complicated. So one way you could do it is break up the input, do something to each block, the same thing, and then do some linear thing overall. And for some reason, we've all decided that this is what we're all gonna store our credit card, whatever, information on.
Pretty much.
Well, the people have tried to break it for a number of years. There was a competition for it, which lasted like several years. And it's actually very easy.
Yeah, okay, so I'm trying to add for comedic effect this thing, but to be fair, why do we think LWE or DDH or whatever are secure? It's because nobody broke it. Well, actually, there's more people that try to break AES.
Yeah,
So, in that regard, AES is more secure.
So the S's are small permutation boxes in the same sense, right? B-bit permutation boxes.
Yeah, so it's going to be smaller. And we're going to see one of the favorite choices for this is going to be the inverse. So if you think of this as just an element of F2 to the 8, or F2 to the B, sorry, it's just the inverse over the field. So it's an easy to describe permutation.
But I mean, are we meant to think that n is growing, but a b is constant?
No, well, okay, so here comes the question of practice versus theory. There are concrete numbers for these things. Where we're trying to get, I don't think I emphasize any specific regime, other than the constants that we care about.
So linear mixing, like do you have both like shift rows and mixed columns in there?
Yeah, well, so shift rows and mixed columns is linear mixing, right? And so I have it like this for now. So for AES, for example, it would have been a 16 by 16 matrix, whereas for liberating to shift rows and mixed columns to make it simpler. But yeah, I'm gonna mostly.
Is it that
cover
in the
it.
last round they apply only one of the two or something?
Yeah, so they don't apply most of the mixing because it's deterministic, so you can always invert it. So
Yeah.
you don't need to apply the permutation at the last round, which I don't do here either.
And if all these are public, then isn't it easily reversible?
The secret key, so these are public, but the secret key, which is here, I'm gonna show you, by the way, the SPN in its entirety in a bit, so maybe I should do that first, but there's still keys. I'm still XORing with the keys. This is just one of the applies that you apply. So you get some input, you XOR with a key, you do this, you XOR with the next key, you do this, you XOR with the next key, you do this.
So this part is reversible, but other parts.
Yeah, you don't know the key, so how would you? Okay, yeah, so I guess this is what it actually looks like together. So you XOR with the key, you do this thing, XOR, you do this thing, and you keep going. And so this has a bunch of parameters. So this is like the summary. The input length, the number of bits, is n, which is k times b. We split into k blocks, b bits each. And one of the other parameters will be the number of rounds that we repeat. The S box, which is this S here, is the public permutation over b bits. And we have the linear mixing, which, as I said, is a k by k matrix. So now I'm ready to give you the description of AES. And I just need to specify these parameters for you. So AES takes as input 128 bits. It splits them into 16 blocks that are usually arranged in a 4x4 matrix, but that doesn't matter for us. 8 bits each. Number of rounds is 10, 12, or 14. Actually, the 14 is a little bit different. It's other things. Let's forget about it. And the S box is the inverse. So inverse is nice because you need to invert S, and the inverse is its own inverse. So you don't need extra hardware to do the decryption. So that's maybe one of the reasons we like the inverse. And the linear mixing, as someone said, consists of some specific matrices that we will not care about too much.
So it's like matrix multiplication inside that box, the linear box.
Yeah.
And then so to invert the encryption, you can use the exact same hardware.
Yes, well, you need to have the inverse of the linear mixing, but yeah, the exact same pretty much.
Yeah. You have to have the inverses for those linear mixing boxes, yeah.
But it's a fixed mixing, so easy. It's about the. Okay, so now I gave you a more theory-friendly version of AES. So what about the reduction? Now, well, okay, I still don't know any math problems. If you have any ideas, let me know. So if we don't know how to prove a reduction, then what can we do instead? Maybe one idea is, okay, let's do for the next best thing, which is to secure against specific attacks. A reduction will give us security against all possible polytime adversaries. Well, let's just say, okay, what about specific attacks? And that's nice because cryptanalysts have spent a lot of time developing many really good attacks against block ciphers. And I'll just throw some names: differential attacks, linear attacks, square attacks, impossible differential, yo-yo attacks, and multiple of 8. And here comes the T-wise independence part of the talk. Why T-wise independence? Well, it's going to be, actually, let me define T-wise independence first. So we're going to say AES, or permutation, is T-wise independent if the following security game holds. We're going to have the adversary here, and the adversary interacts with a black box that carries a permutation using input-output queries. And in the real world, this box contains AES with a secret key, like the normal execution. In the ideal world, it will contain a uniformly random permutation on ends. And so we give the adversary T non-adaptive queries. You can make them adaptive as well. And we ask that the adversary cannot distinguish in unbounded time. So this is a statistical guarantee with advantage more than 2 to the minus n. So 2 to the minus n might seem restrictive. I think practitioners generally want to say that if you have a secret key of length n, you get n bits of security. And
so by non-adaptive, do you mean the adversary has to query at the same time. I cannot.
Yeah, you have to choose your inputs before, and you're gonna see all of the outputs at once.
Okay.
And here's another definition which says, again, if you choose all of your inputs before x1 up to xt, you're gonna get the outputs y1 up to yt, and you have to look close to the input. And okay, now you may ask why ty-wise independence. That's a very reasonable question. So the main motivation is that it actually protects against a wide range of attacks. Already from t cos 2, so there's pairwise independence, differential attacks, linear attacks, they are covered. If you go to 2 to the d, you get higher degree attacks. So it captures a nice set of attacks that we can guard against. And generally also ty-wise independence guards against any attack that sees t.
That's sorry, what was that last one?
Just ty-wise independence, it captures against any attack that doesn't have necessarily a name, but only sees t inputs.
Yeah, that makes sense. Yeah.
So ty-wise independence is not the goal though. For example, if you want to get ty-wise independence, you can just use polynomials, right? But polynomials are not very good because if you have a degree t polynomial, then you can break it with t plus 1 inputs. So this is more like a proxy of we want to show something is ty-wise independent and it's also plausibly pseudo-random. Also, this was said to me by someone who's closer to the practice side. Ty-wise independence gives you a nice metric that you can compare block ciphers. So one could make the argument that if block cipher A reaches ty-wise independence faster than block cipher B, then maybe block cipher A is more secure for some.
Faster in terms of number of rounds.
Yes, it needs less rounds to reach ty-wise independence. Another thing is that there is a conjecture, which if you want you can believe, if you don't, that's fine. But a block cipher that is 4-wise independent should also be pseudo-random, so another reason to study t-wise independence.
Is there any reason they conjecture this?
It's just because we know it's false for t cos 3, and
Oh.
we don't know how to show it for t cos 4, which my understanding is that this is how things go in t sets.
Okay, alright.
Okay, and I mean, obviously, this is also what we can show. We can show things about t-wise independence, so another reason we care. Okay, so let me tell you about some results on SPM. And our goal would be to apply those to AES specifically, but let's study the general thing first. So these are results from the collaborators before I joined the project. This is Tianan Liu, Stefano De Saro, and Vinod Kanathan. They studied the pairwise independence of SPNs, and they got some results for 2-round and 3-round SPNs. And so recall that for AES, the number of blocks, which is k, is 16, and the number of bits in each block is 8. So already the first theorem gives you something vacuous because it's a distance more than 1. So anyway, you need to use 3 rounds at least to show at least some closeness to pairwise independent.
Which implementation of the permutation? Literally with this linear mixing?
Yeah, so so for the linear mixing, I say here that they assume maximum branch number, which is, I guess, something related to MDS codes, but you can think of it as it doesn't have too many zeros. So it's not like a solid mixing that just passes through as it is. For the S blocks, I should have mentioned this, they assume the inverse S blocks, which is the same for AES. So you apply a bunch of inverses to each block, you apply some linear mixing, and then.
So what do they assume about the linear mixing here? I actually didn't fully understand what linear mixing is. I just take it to be like multiplied by a random matrix.
Multiplied by a matrix, it's a fixed matrix. So you should think of it as, yeah, basically if you here's the actual condition.
Yeah.
If you multiply a vector that has many zeros with this matrix, the output will have few zeros.
I see.
And that's nice. It's a nice property, and it seems to be sufficient / necessary for.
Doesn't this like tell you something? Because like if this, or maybe because you XOR, so it doesn't tell you something. But like if you didn't, then you could start with something with very few zeros, go to high zeros, go to few zeros again,
Yeah,
go to high zeros, and at the end, like if you know that you applied like an even number, you might be like, oh, there was a few zeros to start with or something.
Yeah, so we're gonna see that going to many zeros helps. We're gonna see in the proof how going to many zeros, it's like a generic state that mixes very fast.
Okay.
Yeah, okay, so this condition for the mixing doesn't hold for AES because they want to make it more efficient. So it actually has a bunch of zeros, the mixing of AS. So, okay, all this worked for nothing. So we had to work even more to get some result for AS. And the theorem they got is that 6 rounds of AS is 0.42 close to pairwise independent. And 0.42472 is a specific number. Why? Because you can use an amplification lemma, which says that if you have something that's epsilon close to pairwise independent, or T-wise independent specific generally, then if you compose it with itself, so it's nice because block ciphers have rounds, so you can compose them with itself by just increasing the number of rounds, then the difference goes down, the distance from T-wise goes down almost exponentially. The problem here is that there is this 2 factor, so if epsilon is a half, you can see that it doesn't go down, and this is tight, you can't go down if you have a half. That's why the bunch of work to get to slightly less than half. And so applying this amplification lemma gives you that 6 rounds is blah 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 pairwise, and to get the desired level of security, we need to repeat 9,000 times. So AS is 10 or 12 rounds. So, okay, I think this is like the first concrete bound for AS, but 9,000, okay, it's far removed from reality. And actually, when I presented this at Crypto, I made a little bit of fun to show our result, but then I realized our result is also not 10, so maybe I should tone it down a little bit and be respectful to other people.
But also, is it like, maybe you know that AES is like secure against like differential attacks? Like these like specific attacks that are implied by T-wise independence?
Mm-hmm.
So how do they know that AES is secure against those attacks?
The thing is that the analysis community, they don't follow, I guess, the same rigor that we follow with proofs. So they assume independence many times. So even if they have proofs that it's secure against differential attacks, they wouldn't probably, they wouldn't probably satisfy correlation. But yeah, there are many differential analyses. I imagine of AES, not familiar with.
Question? So what is pairwise independent?
2-wise independence.
Well, Did you define epsilon close? I guess I missed it.
It's toleration distance. Maybe I didn't actually. In toleration distance, so you get you have 2 distributions and what is it?
Wait, is this like the definition you had? This
Yeah, that's the one. Yeah.
Oh, okay.
So
you
the
do have it.
distribution of y1 up to it over the choice of random key is the distribution over t2 both of outputs. This should be close to uniform. So it's as if you're seeing t-dependent inputs,
Wait, so
with the caveat that they have to be different.
epsilon can't be 0 unless it's like actually a fully uniform function or something like that. Right?
Yeah, sure.
Why not? I mean, polynomials are not like truly uniform, but they are T-wise independence perfectly.
Yeah, it's possible that epsilon is 0, but not for. I see. Okay.
Yeah.
So there are some results about some designs, right? That you can't have like a fork design with some structure.
I don't even know what the design is.
I think only 2 and 3 Ys might be.
Yeah, that's.
4 Ys with epsilon is 0 is not. Something like that.
I'm also superficially familiar with this, but
Yeah, no, I don't know.
typically getting to 0 is a little bit too hard, harder than it should. Okay, so 9,000 rounds. Okay, so then maybe the question is, can we get is 9,000 maybe to a lower number?
So here, do you assume, for this group, do they assume like the S boxes are some kind of like ideal?
No, so for this one we assume the inverse S box. And that's actually why the analysis gets heavy, because you have to analyze these inverses with classes. It gets weird. They use some nice Fourier stuff, but still there is error terms here and there. So
And do you have like all the mixing layers for this?
all the
For the 9,000 layer, 9,000 round, like you have the mixing layer, because it gets much more complicated, right? You have the linear mixing, or because I've seen people often remove the mixing layers in analysis.
yeah. So this is coming up, but for this one it's the complete SP. So yeah, the starting point for it is the next work, whose goal was to lower the number of rounds, is to use this more idealized model called the SPN star, which I will describe soon. And okay, so recall SPN, this is how it looks. And now we're gonna have SPN star, where we just replace the S box, that was the inverse, with just a uniformly random permutation over 8 bits. And so it's gonna be secret, so it's gonna be part of the secret key now. this adds way too much randomness. This makes the model significantly much more powerful, but because it's nicer, it allows you to get a tighter analysis and get better things.
You can just generate the randomness with AES. Okay.
Use a small AES for the big one.
Yeah.
That would be nice. Okay, so this is how the SPN looks like now, and then we're going to replace this S, which usually are inverses, with secret S boxes, and because they're secret, they're going to be part of the key now. And well, because you have random here, this XOR doesn't do anything, you can just forget about it, and it even makes the SPN star secret. So this is how now the block cipher will look like. You get your input, K blocks of B bits, you apply random permutation to each block, you apply the linear mixing, you apply fresh random permutations to each block, and you keep going.
So each S is independent sample.
Independent uniform example. Very, very, very strong model. So, yeah, you may ask, what is this? You're using way too much randomness. Well, first of all, there exist some block ciphers with random S boxes, so it's out there. And also, we can actually translate random S box results to non-random S box results. This is what we call censored SPN, and we're going to see in a little bit more closely. But the main lemma is that if you just compose add round key, so it's the operation that just XORs the round key, with inverse enough times, then this becomes a random permutation. So you can just kind of simulate a random permutation by doing enough inverses. So maybe it's not too bad. What's part? It's add round key. It's just the operation where you add the round key. And I actually have a picture here. Mm-hmm. So this is where you XOR the key, you do inverse, XOR the key, you do inverse. So this at some point looks like you're applying a random permutation to each one of the blocks separately. Mm-hmm. There is no mixing here, note, so the blocks don't mix between.
It's the same amount of entropy though, right?
What do you mean?
Like the number of random bits that you use to do this arc games, like you need to do this a lot of times, right?
Yeah.
So I assume maybe the amount of times you did this, like the number of random bits that you need to do this, you could also just generate a uniform random permutation with it. Right?
Like, is that true?
Yeah.
Did you de-randomize? Did you decrease the randomness?
No. Yeah, we're not saving anything. It's just it's for. We're not trying to save randomness here. It's just it makes it easier to analyze. That's why we're looking at that. Not only that, we're just batching a bunch of inverses and we're saying, okay, they look like they're random now. Yeah, we're not trying to say anything in the randomization.
Is the savings in the number of rounds somehow accounted for by the fact that you're sort of implicitly doing many rounds to get a single round?
Yeah. So I'm gonna tell you, if I'm counting randomness boxes, I'm gonna tell you SPN star.
Yeah.
If I'm counting these, I'm gonna tell you SPN. So it's not. I'm not trying to cheat that much. Just a little bit. Well, no, I'm not trying to cheat. I think it's okay. So yeah. And the other thing I wanted to say is that because having this random S box allows you to do a tighter analysis, it gives you some nice observations. So this maximal branching number property that I said about the mixing, it pops up in the analysis, and it seems that the closer it is to optimal, the better your convergence is. And also, we get some bounds that show how different parameters, for example, the number of blocks, affects the convergence. Whereas prior results, the more number of blocks you have, because we are doing some union bound stuff, it was worse. Whereas with our thing, it seems that K helps. More number of blocks helps. Okay, and so the results that we have can be summarized in the form this number of rounds of SPN star suffice to reach epsilon close to as independence. And it's basically 3 types of results, and then this one you can get by amplifying this. And the reason I have this red here is because there is 3 parameters, and you can choose your favorite result depending on what parameter you're willing to sacrifice. So if you don't care about constant t, you can use the top one, where only 2 rounds suffice to get very close to two-wise independence. Another point that random S boxes are very strong, just 2 rounds is enough. If you are okay with not getting too close and doing amplification, you can get some other larger t, and you can also get log t for more rounds. Yeah, you can also sacrifice the number of rounds and go log t. So something that I want to say here is that note that the number of the T-wise independence goes up to at most square root of 2 to the b, whereas it shouldn't be, right? In principle, you should be able to go up to 2 to the n, which is 2 to the kb. But for some reason, because the analysis, it has to deal with collisions and things being equal, etc., and because when we break them into blocks, now we care about collisions within the block that only has 2 to the b elements, the analysis it just seems to get stuck at square root of 2 to the b, and it shouldn't be, and it's very annoying. So if anyone has any ideas on how to get over this, I'll be very happy to hear. Okay, so we can now get this analysis and go back to AES. And we're gonna first go into AES star, which is AES when we replace the inverse with random S boxes. Honestly, it's just an SPN star with specific parameters. And we can compute exactly its convergence properties now. 7 rounds of AES star, for example, is very close to pairwise independent. And oh, by the way, this is using some calculations that were done from beforehand by Bourgeon and Bodeny from 2006. And this result is actually tight. It was numerically verified. You can compute things exactly, and 6 rounds of AES star is not that close, whereas 7 rounds of AES star passes the threshold.
So how is this calculated? Like somebody managed to
You write the program, yeah.
give a
You can-
distinguisher, like you just like, but you can't run, oh, so you ran the program 6 times, and maybe for 6 rounds, and then you ran it, I don't know, like 52 to the 50 many times, and then you plotted it, and you were like, oh, actually these two things are correlated to each other? Like, is this gonna?
No, so you can't, because when you have these random S-box, things become really nice. And you can basically just look at things as a Markov chain.
Mhm.
And this Markov chain, because you have layouts, there's sort of symmetries, you can project things down to smaller things. You can actually write the whole transition matrix. It's a little bit big, but you can do it, and you can compute the exact transition probabilities, and you can compute 7th power and see that the distance is at most to the -128.
I see.
And okay, so now we have the result for AES star. And what about inverse S boxes? We're going to use the trick that we used before, where we get a random S box and we unroll it into inverses. And doing this, we get that 192 rounds of AES is close to pairwise independent. So here I say censored because when we unroll the random S boxes, we skip the mixings. So this is why it's censored. We skip many of the mixings, actually. And it's, oh, my measure here broke. Okay, I'm gonna tell you more about censored SPN now. So let me try this thing. Okay, so animation is broken, but here is an SPN star at the top. And I'm gonna show you how we unroll the random S boxes into inverses. So we get one layer of random S boxes. Is there a question? Sorry.
I know, it's like the thing that you showed before, right? You said, oh, you apply like arc in
Yeah.
existing, right?
Now I'm gonna put into this SPN to show that mixings are missing. Some mixings are missing. So yeah, it's exactly what I showed before. And here I have shaded out the mixings because there is no mixing in what I showed before. And so you can see that there's inverse, no mixing, inverse, no mixing, inverse, no mixing. Then there's a mixing there. And then we start the next one, no mixing, no mixing, no mixing, inverse there. So the censored SPN is an SPN where a large number of its mixings are missing. Yeah, that's using the lemma I wrote there. And this is how it could look like. You're missing 2 mixings, one is there, you're missing the next 2.
So because it's only epsilon close, is that like a problem and you need to like propagate this epsilon, right? Because you're doing this not only once, you're doing this
You
many
do
times.
yeah. So you
And
have
you
to be
get worse
careful.
and worse.
And that's one of the reasons also that 7 rounds of AES star becomes 192.
I see.
Big increase.
So is this result, because this seems like pretty much like maybe easier to analyze than the whole thing, like how close this is to random permutation. Like is the epsilon bound that you guys have for this like tight?
That was also, so we have a bound for this, but for the specific parameters of AES, you can again compute it numerically. And we
I
get
see,
the-
so yeah, it is tight,
the
it's
bound.
just what it is, yeah.
The analysis may, you use some union bound and stuff, so maybe that is not very tight when you putting them together, but
But just each individual component is tight, but then putting them together isn't.
yeah. I mean, I don't know, maybe 192 rounds is needed. Who knows?
Yeah, I don't know.
Okay, so then this is the theorem that we said before, and what I'm trying to say here is that we remove many mixing layers, and mixing layers are useful. If you have no mixing layers, then you really don't mix. So censored AES should be weaker than normal AES. So if 192 is good enough, then 192 of censored AES is good enough, then probably 200 of true AES should also be enough. And yeah, so that's some improvement from the 9,000. Yeah, so that's pairwise. That's just it. Okay, so I have some terminal details, but it's already 4:42. So if it's okay with you, I'm gonna skip them, and I'm gonna talk about the reversible circuits. And maybe we'll have time at the end of Q1, we can look maybe at one of the things that I have. Okay, so the reason I want to also talk about the reversible circuits is because it's kind of a new model, and well, Ryan and William worked on it as well, so it's a very nice natural model, and it seems to be gaining traction recently, and it's interesting to see what it has. So, an emerging block cipher, reversible circuit. So, this is another way to get a key permutation on n bits. Recall before I told you we go in rounds, every round we do something, it's the same thing, but now every round is just one random gate, and this is also part of your secret key. So, your secret key at round 0 is going to be the first gate, the location of the gate, and the permutation it computes. And then the next secret key is going to be the next gate, etc. And by saying a gate, you can think of a random 3-bit permutation, a random gate that computes such a random 3-bit permutation. Or you can think of some subset, but let's think of a random 3-bit permutation. And yeah, so now for example, key 0, as I said, is this random permutation of 3 bits, and the wires it acts on. So this one is going to be, I don't know, the identity on wires 7, 8, and 9. This one is going to be flip 2 and 3 on wires 5, 6, and 7, etc. And they don't even have to be consecutive, they can skip wires. So, well, for some definition of block cipher, that's a reasonable block cipher. And we can ask the same question that we're asking about SPNs. We have this circuit. How many rounds do you need to get TY's independent permutation? And let me give you some background because it has a nice story. I will say that Ryan has a video on reversible circuits about Tim Gowers' on the occasion, I think, of Tim Gowers' birthday. So it's a good video, you should watch it. So Tim Gowers in 1996 introduced them to study the problem, the previous 20 question. And he studied the TY's independence of these circuits, and then some subsequent work by some other people. They improved some bounds, and I think one of the good bounds they have is that n squared, n is the number of wires, I don't think I mentioned it, times t squared times log 1 over epsilon gates suffice to reach epsilon close to TY's independence. And also quantum physicists, they like to study the circuits, the quantum version of them, where you put random gates on your qubits. We have a bunch of connections they don't know about to quantum state randomness, black holes, and many body systems. And also very recently, Ram Kennedy, who's a cryptographer, along with some statistical physicists, I believe, they try to use these reversible circuits to get more advanced cryptographic primitives. So they say, let's assume that reversible circuits are pseudorandom, which we don't know, but let's at least assume this baseline. And then they give some candidate obfuscation schemes, how to get obfuscation by moving gates around and everything. And yeah, because it's with physicists, the whole scheme is inspired by some thermalizing process of statistical mechanics. I will also say that, as I said, Ryan and William study these circuits, and one of the nice things they do is that they study a more structured version of the circuits, where the gates now are not thrown uniformly at random. They have to be a little bit more structured, called nearest neighbor. This one is the brickwork architecture, where you put a bunch of nearest neighbor together. And if we want to make the argument that block ciphers are for practicality, well, this is actually something that you can implement, right? Nobody's going to put random wires and random gates on the wires, whereas this one, you can actually make the case that it can be implemented. So Definitely a good model, and I think there's going to be a theory lunch talk about this soon, so stay tuned for that. But back to what we did with William and Luke, is we showed that for t, not too large, but still exponentially large in n, a random reversible circuit with nt times log 1 over epsilon gates is epsilon close to t-wise independent. We should compare this with the bound that I showed before, where it's m squared t squared. There is some other bounds as well. So the analysis that we use uses log Sobolev inequalities compared to spectral gap analysis, which was the technique of the prior work. And log Sobolev allowed us to get rid of some of the extra n, t factors, so that was nice. And it's also optimal up to polylogs for constant epsilon. And it's not hard to see because the number of t-wise independent permutations is roughly n to the t. So how many bits do you need? Well, roughly, I guess, 2 to the nt. So number of bits that you need is roughly nt. So for constant epsilon, that's very good. If you want to get epsilon to be very, very low, so exponentially small, then this log 1 over epsilon will bite you and will give you some extra polynomial factors. So it's not optimal in that regime, but for constant epsilon, you can hope to get better. And
Out of curiosity, I guess I'm assuming that the spectral gap you just like are like, oh, it's like a random graph. You can try to use like spectral methods to show that things mix well, kind of vibe. But like, what's log Sobolev? I'm not familiar with that.
it's a similar thing. So you can think of spectral gap as trying to bound the decrease of the variance as you walk in the random, as you follow your random walk in the Markov chain. Whereas log Sobolev tries to bound the decrease in another quantity eventually. And I guess
What's the other quantity? Did you say it's an
entropy.
entropy?
Is very rough, but it's an entropy. And I guess the good thing is that entropy starts from a lower value than the variance. That's why it gets faster, goes down faster, which allows you to prove a better bound. But as you're trying to get epsilon down to exponentially small, it matches the spectral gap. That's why for very small epsilon, our result doesn't get any improvement. But for constant epsilon, it gives you something. So one of the nice freebies from this work was that we learned that this result gives you something else for free. The following corollary, that if you sample a random circuit with L gates, then you cannot compress the circuit without losing functionality to less than L over n cubed. And this is, it's related to the incompressibility of circuits, and it was pointed out to us by some quantum people that were interested in the same problem.
It's a reversible circuit?
Reversible circuit, yeah. Yeah, reversible.
Because similar things for, I remember talking to William about this one time, like similar things for standard circuits, non-reversible circuits, or like normal circuits are easily known with the counting
Yeah, it's like
argument,
Shannon's-
Shannon arguments, right?
Yeah.
But this is like,
So how would that even go?
I mean,
oh
no.
wait, I actually, no, I remember, sorry, excuse me.
We've
Let
done
me
the same
revise.
thing today,
A
too.
random a random function can't be compressed.
Yeah, but so this is a different
Yes,
statement.
yes,
Different
okay.
statement, yeah. Honestly, yeah, I didn't know that was a question. You're right, it's a bit subtle.
Yeah.
The difference is subtle. But yeah, well, that's it. And I guess Ryan today mentioned that, I guess we don't know if this is tight. I don't think we have any reason to expect this is tight. Probably you can, the n cubed, you can probably improve it to n at least, but maybe the log. Yeah, so that concludes the reversible circuits part of the talk. Okay, so I'm going to give you some open questions and then we can open the floor. So many t-wise independent questions remain. The first one would be, can we get the t-wise independence of any non-idealized log cipher for larger than pairwise? So note that the first results I showed to you were for pairwise independence and also for AS. And the ones that were for general T were for the idealized cipher, which makes it easier. But for the SPN with the inverse S-box, we don't have any such results. I would say if you really had to, you could probably get such results for T plus 3, T plus 4 or something. but it's gonna be high key. So I don't know. There's probably a better way to understand TY's independence for SPMs without inverses, with inverses. And yeah, obviously, okay, can we improve the analysis on AS? 192 rounds is still really far from 10. If you have any hope to getting it down to 10. And yeah, the other thing which is my personal favorite problem is, even for SPM star, we can get to T up to square root of 2 to the B. This shouldn't be the case. There is no reason to stop at the block size. I already give you something that's 2 to the B wise independent, the uniform random permutation. You should be able to get more than that. So I don't know. And it seems that this type of birthday bound type of things, they show up in other analyses as well. So it seems like it's there's a barrier there. There's an obstacle that we don't know how to overcome. If you generally like block ciphers, and I hope you did, can we show reversible circuits are super random, or basically anything about reversible circuit? Yeah, so there's also, can we study other kinds of attacks? And one of my favorite examples of this is this paper by Benny Applebaum and Shaharlovet, where they used the polynomial calculus proof system to show some lower bounds on algebraic attacks. And finally, I touched on this a little bit. We assumed so far that the secret key has independent keys per round. This is not the case. You usually have the key scheduler to expand one key to many keys. And sure, we can squint and say the key scheduler is a PRG. It's very far from a PRG. So what properties from the key scheduler do we need? If I know it's secure, if I know my block cipher is secure with independent keys, what's the property for the key scheduler that's enough to give me security for even with the key scheduler? Okay, and then, generally this research program that I got joined in when I was doing my master's with Rijndael, and the goal is to study complete classes of block cipher attacks. And TY's independence is a nice thing. We can prove things about it. It cancels some of the attacks that we know. That's great, but there's so many open problems. And it's an important quest, understanding practical encryption schemes. Cryptography, theoretical cryptography has gone miles forward. We have crazy primitives, and we're stuck at symmetric key crypto in the block cipher world. So it's kind of unfair. We should give symmetric key crypto some love as well. And yeah, what's nice is that it's really the wide world. So maybe there is space for new math to be developed. Who knows? So that's all for my talk. Thank you for